I would like to welcome you to the MnRI series. We are very happy to have Professor Hyun Soo Park giving a talk about neural human geometry, reconstructing humans in 3D from a single imaging. Hyun Soo is assistant professor in the Department of Computer Science and Engineering at the University of Minnesota. He's interested in computer vision for behavioral imaging and analysis. He's the recipient of the Career Award and also the CRII Award. And he received his Ph.D. from Carnegie Mellon University. And he did his postdoc at Grasp Lab at the University of Pennsylvania. So without further ado, Hyun Soo.
All right, can you hear me?
Yes.
Right. So thank you for introduction. I'm Hyun Soo. Again, I'm assistant professor at computer science and engineering. And here in this talk, I'd like to share my research on the neurohuman geometry, reconstructing humans in 3D from a single image. So note that this presentation focuses on very recent work, including many unpublished work. So let me begin my talk with one of the book that I like, The Plague by Albert Camus. Although the book was written in 1947, it's so amazing that the depiction is very close to what is happening now, caused by this, the COVID-19, and how people react to this unprecedented circumstances, and how government get lost their control and hide information, and how smart citizens come up with their own solution to fight back to the virus. And among this, one of the things that I like was, the way he described the lockdown. One of the most striking consequences of the closing the gate was, in fact, the certain deprivation befalling people, mothers, children, lovers, husbands, and wives. Unfortunately, after 70 years now, despite the technological advances, we are still suffering from social disconnection caused by this lockdown. So it is so great that we have a video conferencing software such as Zoom that was developed before the pandemic, so we can keep doing the social interactions and collaborations. So let's see what it can do. So while Ryan is speaking, Ryan is observing the smile face of Jessica and indicating she's agreeing with him. And he can even detect the intent of the Jeff who is about to speak through these videos. In other words, we can visually transmit and receive the social signals, such as a facial expression, gaze direction, and gesture, which are very subtle and microscopic signals through these videos. However, because of the nature of this 2D video, we cannot really control the viewpoint, which significantly reduces the sensation of the social presence. So in the meantime, AR, VR immersive technology to provide the viewpoint control, okay, that adds new sensation of the social presence. So you may already have seen this video by the Facebook. Okay. This illustrates their future product of the social interaction in an AR and VR environment, where you can control viewpoint as the viewpoint change according to the way the glass wearer move. And it is so compelling, and I believe this technology is about to deploy in our the everyday lives. However, you notice that the person is replaced by the virtual character that does not convey photographic visual sensation. We cannot observe that subtle the facial expression and gestures through these videos. So in sum, existing the AR and VR allows active view control, but it limits fidelity a lot. The question is, why is it so difficult? Why is it so difficult to build some platform that allows this both high fidelity and active view control? So By the way, I want this presentation to be interactive, so you please feel free to stop me anytime. Okay? So the challenge of this stems from some interesting phenomena about our perception called uncanny valley. So let's consider that this x-axis represent the human likeness. So 0 means there's like no visual similarity with humans, and 100% means it is photorealistic. And y-axis represent the perceptual affinity. How do I like the avatar? So for instance, the Wall-E character, the abstractizes human shape, which shows almost like a neutral affinity.
Hyun Soo,
Yes?
are you presenting? I cannot see any of the presentation. Is everyone can see the presentation?
I can see it.
Yeah, I can see it.
See it right now as well.
I can see it.
Okay, thank you.
Yeah, we can see it.
Okay. All good?
Yes. Yes, go ahead.
Okay. So again, the Wall-E character abstractize the way we look, and it shows like the almost like neutral affinity. And when avatar becomes like more like a humans, and then we feel more empathy and sympathy, resulting in better affinity. So of course, like if we see the photographic avatar, photorealistic avatar, then we see the true human, and which we like to interact, and we get this true sense of sensation of the social presence. So if I just interpolate this data point, and this is the curve that I see, but the trend does not really scale in this way. There is a strange reasons between the cartoonish character and the photorealistic character. And this reason, people feel creepy about the character, and they don't like the character, and they cannot really engage when they interact with. And this is called the uncanny valley, hypothesized by the Japanese roboticist Masahiro Mori. And it is, there's a lot of implications on this developing platform for the social presence. And this trend even amplified when involved with motion. Okay, so on the bottom of this valley, that corresponds to the jungle. So, the Dr. Mori actually recommend that the designer must take into focus on the first peak of their goal, which is like this cartoonish character, instead of risking falling into the uncanny valley. So the virtual character that is used for this Facebook demo, that will actually fall into like first pick of this uncanny valley. Even though you want to increase the likeness, human likeness, we always need to take a risk of the falling into this uncanny valley. So, however, but what we want is, as shown from the Zoom example, we want this photorealistic avatar that can convey our social interaction, social signals, microscopic social signals through the video. So actually, there's a lot of work to overcome these challenges. So for instance, the light stage designed by the Paul Beverbeck allows you capturing these high fidelity humans. It can capture the porous level skins and fine hairs from the light stage, and it has been applied to the movie industry to create the special effect. Another instance will be the multi-camera system from the Face Reality Lab, using the hundreds of cameras. On the right, I'm showing the rendered avatar, which is almost indistinguishable from the real video. So in sum, this system leverages massive sensing infrastructure to reconstruct the precise geometry of humans. However, because of this requirement of the infrastructure, this is very difficult to deploy in real life. So the question is, can we produce high fidelity reconstruction using a single camera? And then I found that this question is contradictory because the high fidelity is only offered by the multiple cameras. Okay? And you need and single camera cannot really achieve this. So my intuition to approach this problem is, yeah, we're going to leverage machine learning. We're going to use a machine learning to fill the gap between the multi-camera system and the single camera. So this is what I'm going to talk about now. So any questions so far? Okay. So for instance, the given a monocular video person, we reconstruct a high fidelity avatar that is almost compatible, comparable to the avatar that created by the multi-camera system. So you see that this small wrinkle that is reconstructed and rendered. This is actually captured from my cell phone. So let's see how this multi-camera system works and then move on to the single cameras. So given the set of image captured by the multiple view image, multiple cameras, so which I'm going to denote that as X. The goal is to render X head on the right, okay, so that we can display on VR glasses. And this is a classic signal processing pipeline where you have an encoder that compress the signal X to form a compressed code Z. And that is decoded by the decoder that reconstructs the original signal X. The main assumption about this is that your signal lies in the low dimensional manifold so that we can actually reconstruct the low dimensional space from the input data. So here, instead of sending the raw video, we are going to encapsulate all this information into the texture and geometry. Okay, so so we are sending the texture and geometry, and then we decode the texture and geometry again to display in the VR glasses. So that's like a pipeline that I'm going to present. So let's consider the decoder first. So a simple form of decoder can be the linear decoder. Okay, and this is nothing but a matrix where there is column space that spans the high dimensional the input texture and the geometry. Okay. These are the matrix that can decode from the compressed code Z. For the encoder, you have a similar matrix E that can project the high dimensional input to the low dimensional Z. Okay. And then, as we learned from the linear algebra, this is nothing but the PCA decomposition. Okay. And we can decompose the matrix, the input the matrix X into the decoder and encoder. So now, this is like a simple form of the encoder and decoder systems. And of course, now this is a deep learning era that we can write a paper with the PCA. We can encode this using the neural network called the variational autoencode, which is nothing but a nonlinear PCA. Again, the idea is the same. So you get the input X and compress to form the compressed code Z, and then Z is again decoded to produce an X hat. So what is so interesting about this variational encoder is that it's a flexibility. You can actually, we can add the additional variable, which is a viewpoint, so that it forms a conditional variational encoder. So your output is a condition on the viewpoint. because your appearance can change according to the viewpoint due to the illumination and the translucent surface scatterings. So now I just formed the variation encoder and variation autoencoder condition on this viewpoint. The question is, how can we replace this multiple, the texture and geometry obtained by the multiple camera to the single images? So what we did was very simple. Like we just come up with the new monocular image encoder based on a convolutional neural network that can generate the equivalent latent code Z. Okay? And in addition to that, we actually trained another regressor that can regress the viewpoint so that now we can even condition on the viewpoint as well. So by combining this, we can train the image encoder and the viewpoint encoder that can actually now take the single image, monocular image captured from your cell phone, and to produce a texture and geometry that can be rendered in the UV. So here I'm showing the sum of result that on the left, I'm showing the input video. Here this is the geometry overlay with the image, and this is the texture that is rendered in that view. And unfortunately, this naive implementation produces undesirable reconstruction that produces unstable facial trackings. You see that a lot of jitter when we actually reconstruct the face. So the main, this is actually caused by the domain difference between the training data and your testing data. So the training data is is the one that captured from the laboratory setup, and the testing data from your cell phone. Okay? So visual statistics is a completely different, the background are different, the skin colors are different, and expressions are different and so on. So to mitigate this domain difference, so we present a self-supervised framework by leveraging the temporal consistency. So here, we take the input image at time instance t, okay? Go through this autoencoder that produces geometry. Okay? On your right, I'm showing the geometry, 3D geometry of this person. Okay? And then using this geometry, we can unwarp this image to form the online textures. Our hypothesis is that this online texture must be consistent across a time, so that we can, by minimizing the difference between the online texture, we can refine this image encoder such that it can adapt to the testing scene. So this is a self-supervised method in the testing phase. So here I'm showing the illustration of the comparison between this without self-supervision and this is self-supervision with the self-supervision. You see a lot of unstable tracking, and the skin colors are not reflective of the reals. And by adapting to the online texture, we can adapting to the testing domain, we can have a much better tracking and reconstruction. And this is another result that in high fidelity reconstruction from face from unconstrained monocular camera. So all the videos are captured from the cell phone camera, and then you can even render multiple view videos from the single view. So yeah, so any questions so far? I mean, this is, I'm going to shifting gear to the different work. So it's good for you guys can ask questions.
Hyun Soo, are you fixing the angle, the view angle for the reconstruction?
What do you mean by fixing the view angle?
So you're reconstructing from an view angle, right? Like front or side view, or
Yep.
right? So you're fixing so when you when you're training, I mean, when you're reconstructing or when you're testing, you can select whatever view angle that you want.
Yes, so the resultant of this autoencoder is giving you the texture and full 3D geometry. So you can render from any viewpoint. Okay, but for the input that you have to, we estimate the input viewpoint, and is the latent representation. Does that answer your question?
Yes. And when you're training from several people?
No, this is specific to each person.
Oh, okay. Thank you.
And that's not what I'm going to talk about now. Okay, that's a really good question.
I have a quick question.
Okay.
Is the whole pipeline trained all at once, or is it trained in pieces?
What do you mean the pieces?
Like the autoencoder decoder part, is that trained together with this difference minimization?
So the decoder is not trained at all.
Gotcha.
We only train the decoder is actually trained with the multi-view camera system.
Okay.
Right. So we don't touch decoder. I mean, we just replace this encoder that can match to this decoder.
Gotcha.
Okay. Any other question?
I have a question. How do you get the 3D models?
So again, that is from the decoders. That is trained with the multi-view camera system where you have access to the geometry and textures. Okay.
So your input to the system is the 3D geometry and the 3D texture of your faces.
That was a multi-view settings. That was a multi-view setting. Let me just go back to that slide. Can you see the slide?
Yes.
Yeah. So with the multi-view camera system setup, where you can have like a full textures and the geometry. Okay? You have all access, and then you decode the texture and geometry again. Okay. And when we introduce a monocular camera, we don't train the decoder. So whatever latent code we feed into the decoder, it will produce a texture and geometry where you can render in the VR.
Okay.
What we actually train is this image encoder that can take a single image to produce this latent code and the viewpoint. Am I answering your question?
Yes.
Hello? Okay, so then let me move on to that slide. So, so far I've talked about how to approximate the quality of multi-view camera systems with machine learning, by integrating machine learning. Okay, so, but still, this is restricted because, as Saad mentioned, that I mean, we train this for each person. Okay? This person to render should be the pre-scan before with a large multi-view camera system. So these two persons should be identical. Okay, so your network is specified for this person. So the question is, can we generalize this to the new subsets, okay, which will eliminate the pre-scanning then? Okay. So, and then actually it requires a new resources to because the network is only trained for this specific person. In fact, it requires a large amount of the diverse humans that can span all diverse appearance and identity and shape, okay, from the many viewpoints, such that the neural network can encode the many peoples. So the question is, how do we get this data from? So we found a very interesting, unique opportunity, data collection opportunity from the Minnesota State Fair. Okay? So this is like a large social event that attracts like 2 million of people. So we actually leverage this opportunity that we place the multi-camera systems at the State Fair. We build a camera system with in the aid of my students' help. So you see that this is the whole cameras, and this is a display that can synchronize these cameras, and you have a lighting and so on. And this is how does it look like. Okay, when you get into the stage, there's a light and there's a display that instructs you what you need to do. And you see that there's people are lined up to be scanned. They want to participate in this research. Right, so here I'm showing some of example videos. This is input video from 1 view, 4 views, and hundreds of views. And we scan many subjects, which result in this about the 770 subjects. So we can cover many diverse the appearance, shape, and identity. So here to give us some idea that we have well-balanced genders in the data set. We have the age. We have a lot of participants from the teenagers to the 20s, and about the colors, skin colors, and clothes types, and so on. So we can cover the diverse set of human appearance and shape from this data. So given this camera, we can do the 3D reconstruction. You see that the point cloud is reconstructed by this. And specifically, we're looking look at the 5 different expressions: gaze, face, hand, body, and garment. Okay. So to gaze capture, we ask the subjects to look at the one of markers on the scene, okay, so that we can calibrate where this person is looking at. And so as a result, we can get the ground truth gaze, 3D gaze for each person. And this on the left, left top, I'm showing the image of the eye regions, and this is the appearance that is registered in the match, 3D match. So, and on the right bottom, I'm showing the appearance variation across the view. And this is, again, the face, for the face images, and this is the appearance, okay, registered by this mesh model. And on the right bottom, I'm showing the appearance variation across the view. Okay. Note that the appearance change over time, over a view. Okay. And this is 3D hand model. We fit the 3D mesh model called the Nano, where we can reconstruct this 3D mesh, and we ask people to follow the American Sign Language to perform these actions. And finally, we have a body. Well, we reconstructed like 3D body, a mesh model body, and also the garment as well. And you probably already noticed that this subject was the President Gable. Anyway, so now we have data. Okay? So we have data to model the general subject. So for instance, what we can do is given a single view image, we can actually estimate this cross geometry in 3-dimensional space. Okay. So we reconstruct this 3D geometry of t-shirts from this just single view image. Okay. Note that this subject is not scanned using many camera systems. Right, so the way it works is we cast this problem as a 3D mesh fitting problem to the image given the predefined cloth mesh such as the t-shirts. Okay? However, this type of cloth fitting can express a very limited geometrical details of the cloth. Note that the wrinkles on the t-shirts is not really reconstructed at all with this method. So therefore, it is impossible to fit the model or the t-shirts model to describe, to express this historical picture of the Frida Kahlo as shown in the lab. So, with this model, we can actually model the facial geometry and then find details of this drapey scarf. So to mitigate this limited expressibility, we present a method to estimate the depths and surface normal from the single view image. So here you see the single view image of the Frida Kahlo, and this is the depth. The black means closer to the camera, the white means far away. And here we encode the surface normal with the color. And this reconstruction allows us to actually see the person in 3D. So let's see how it works. So consider a single image, and there's underlying 3D geometry of the person. And this problem is nothing but we shoot the ray that passing through some point in the pixels, okay? And that intersect with the 3D geometry. That location is X, Y, Z. Okay? And the depth is defined as a Z coordinate of this X, Y, Z 3D point. Okay, this is how we define the depths. Okay? However, this is a fundamentally ill-posed problem because given a pixel, there's an infinite number of solutions along this array. Given the image, there's a many locations. Actually, infinite number of the solution for this. So the depth estimation is from the single view image is ill-posed problem. And this depth ambiguity can be resolved by leveraging the data similar to the human perceptions. Okay? So we as a human can effortlessly identify the neck is behind the face and hand is in front of her belly and so on. So we have like some understanding, 3D understanding by just looking at a single view image. And actually this can be efficiently learned by the neural network. Okay? So given the input image, we can train the neural network that can produce this output depth. And in fact, this is not an even new problem, right? This is a classic computer vision problem where the researcher have been training a neural network to predict the depths from the single view image for the autonomous driving and the indoor space navigation. So here, this is given the single view image, they reconstruct the depth frame by frame. Okay? This is the most recent work that presented in CVPR. So, okay, so good. So we can use exactly the same idea. Single image fit into the neural network that can produce depths. And the way we train the network is that we have the secret behind this training network is there is a lot of the training data instances with image and corresponding depths. So once you have a lot of these pairs, then you can guide the neural network that can produce this image. So yeah, I mean, with this implementation, yeah, so now you see you can predict the depth somehow and surface normal and the surface visualization on the right. As you see that, it's not really desired. It does not really capture the fine geometry of face. The face are all blurred and the wrinkles are oversmooth. So why this is happening? Actually, this is again the same problem with the problem that I mentioned. disparity between the training and testing data. To avoid, so to give you some intuitions, given a training data, okay, you can have encoding and you can decompose the metrics into the decoders and encoders using a PCA decomposition. So now consider this a decoder that can reconstruct your testing image given this latent code. So here I'm going to illustrate the linear space, okay, linear subspace spanned by the column space of the decoder. Okay? And all the training data actually lies on this linear subspace, okay? Because the D is trained by this training. But your testing data is off from this manifold. Okay? So what you can do is the best approximation will be the projection onto the image, or projection onto this linear subspace, okay, that actually lose all the high frequency details and smoothing. So okay, this projection operation or this approximation approach produce a lot of over smoothing, and it kills all this high frequency details. So this actually, in fact, apply for the deep learning as well. I mean, even though you do the nonlinear embedding, the same idea applies. Okay? So if you have a different distribution between training data and testing data, then you always expect to see this over smooth the result. Okay? So therefore, we need the additional Q to reconstruct the high frequency signal. And then we found that incorporating surface normal is very, very beneficial. The surface normal is defined by the neighboring point that can be computed by the cross product between the two tangential vectors. So this is a tangential vectors under this surface, and if you do the cross product, you get the surface normal. So here I'm showing the surface normal prediction from single view image. Every frame will predict the surface normal independently. Okay? You see that unlike the depth, we can actually reconstruct this small high frequency details from this single view image. So the surface normal is very responsive to this small the texture variance in your image. So what we do is we integrate this surface normal to the depth map estimations. Given a single view image, we compute the depth, okay, that will result in the very smooth, over smooth depth. Then in the same time, we predict the surface normal with the different networks. Okay, and then we fuse this to the coarse depths and the surface normal to produce the fine depths. Okay? And this produces the very high fidelity. And of course, we can self-supervise this predicted depth by taking a derivative, by computing surface normal on this geometry as to match with the predicted surface normal. So this results in the high quality of the depth estimation. In the middle, I'm showing the depths and surface normal. On the top row, the muscles of Dwayne Johnson can be reconstructed. And on the bottom, you see the loose cloth, the t-shirts can be reconstructed. This method. And also we can reconstruct a grayscale image with that capture the drapey shoulder dress here. And of course, we can even reconstruct the Mona Lisa. So that we can see the painting in 3D. Of course, there's a lot of mistake, but we have like some understanding. At least we can reconstruct the depth ordering correct. Right. So here I motivate my talk with social presence that is been allowed by the multi-camera systems. And I present our recent research progress toward the single view reconstruction innovated by the data, machine learning, and geometry. So here I would like to conclude my talk by sharing my view of the social distancing. I believe that to some extent, the social distancing will be becoming the new normal that will impact our lives in many ways. Therefore, the photorealistic, the social presence is more important than ever. So I'd like to acknowledge my team. They are working 24/7. Without their help, nothing is possible. And also, I would like to acknowledge the funding agencies. Thank you.
Thank you.
Thank you. Questions?
Yeah, I have a question about picture that you use for Mona Lisa. How do you decide on that picture what pixel belongs to the person and what pixel belongs to the background? Is this manually done or?
That's a great question. Actually, we use some neural network that can classify the pixel that belongs to human or not. So we pre-process the image to get the mask of human.
Okay.
Other questions?
Hyun Soo, for generalization, what you did is mostly tailored to humans. And if you wanted to move to, let's say, any scene understanding, like the depth image from a car, you have to retrain the network, or can you do like a transfer learning so you can be able to do the estimate, the depth estimation from a driving scene?
Yeah, of course. So those are data is completely different. So you need to retrain it. My focus is on a human, which require a lot of details. But as you can see from the example that I showed before for the autonomous driving, yeah. So in this case, you see that like a lot of like details are actually missing.
Yes.
So for the autonomous driving, you don't need that fine detail of the depth estimation. That's not really that relevant for their task. But for the human, recovering this detail is important.
So you retrained on the whole person, including the body. But if you train only on the face, would you be able to get a much more accurate representation of the face?
Yes, of course. Yes. Yes, if it is only focusing on the face, you will get a much better for the face. The bigger question for that is like, where do you get the training data?
Yes.
Obtaining training data is extremely difficult.
What you mean is the high resolution data of a face, right?
Right. That's not trivial. I mean, you need to have like some massive, again, the sensing infrastructure to do so.
Mm-hmm.
Other questions?
So how do you evaluate the performance of the 3D reconstructions? For example, for this figure that you have on the screen right now, from the paper, how do they evaluate the accuracy of the 3D reconstruction?
So the evaluation is very difficult. I mean, that's a really good question. For those kind of internet image, there's like no way you can evaluate. Okay? You can only qualitatively evaluate. But for this is the data that we captured from the State Fair. Okay? This is a measure observed by the many cameras. So we can reconstruct the geometry, okay, that can help us, that can use for the ground truth. And also we evaluate whether this is a synthetic data. Yeah, synthetic data, we do have a ground truth. So this is the way we can actually evaluate.